Let's say I have a line. Let me make it a straight line. And the equation of that line, since it's running in the horizontal direction, is going to be y is equal to some constant. So let me write that. So the equation of this line right here is y is equal to k. And let's say I have some other point. I'll call that, well, I will call that a focus because it will be a focus. Let's say that point, let's put it right here, is the coordinate, I don't know, let's call it A, comma, B. And let's think about the set of all points, or the locus of all points, that are equidistant to this point right here and this line. And for our, just so you get the terminology, we'll call this line a directrix. Let me write that down. Directrix. It's probably a word you've never heard before. Directrix, and frankly, I've never heard it outside of the context of parabolas or conic sections in general. So let's call that a directrix. This is our focus. And what we want to do is we want to find all of the points in the xy plane that are equidistant to this focus and this directrix. So, there's one point that just by looking at it, we could say is going to be in our locus. So it's going to be right there, because clearly this point is equidistant. It's halfway between that point and this line. Now let's see what other points. There'll probably be this point right here, because the distance from there to there is the same as the distance from if you just drop a line straight down. Remember, we want to get the shortest distance between this point and the line. We could have said something like this distance, but this distance wouldn't be the shortest distance between this point and this line, so you would go straight down to the line there. Likewise, this point would be there, so that distance is the same as that distance. And you could already, I think, begin to imagine the type of shape this is. And if you look at the title of this video, you can probably guess where this is going. That the shape is going to look something like this, or something pretty similar to what we know as a parabola. And actually, it will be a parabola. There's no mystery there. But what we're going to do in this video is actually show you that it is a parabola, show it to you mathematically instead of this little drawing here where I show you that, well, it kind of looks like it would be a parabola because this distance right here looks about the same as that distance right there. Or, I could keep going up and down the curve and keep doing that, but that's not satisfactory. Let's actually mathematically show that the locus of all points that are equidistant to this point and this line, this focus and this directrix, is in fact a parabola. So let's say I have some point that's in this locus, and let me call the point here. Let me do it in a different color because it's the same color as my directrix. xy. So I want to find all of the xy's, all of the points that satisfy an equation where their distance to the focus is equal to their distance to the directrix. So what's the distance between xy and the focus? What's this distance right here? d1. Well, we just used the distance formula. It's x minus the x coordinate of the focus. So it's x minus a squared. So the difference in the x's squared, plus the difference in the y squared, y minus b squared, the square root of that. So this is the distance to the focus. So I'll call that d1. That's this distance right there. And we want to find all of the x and y's where the distance to the focus is equal to the distance to this line right there. So if we call this distance, let's call this the d2, the distance to the directrix. So the distance to the focus is going to be equal to d2. And d2, what's this going to be equal to? Well, it's just the difference in y, right? Because no matter where we are, we're just going to drop down straight to the directrix. So the difference in y, I could just say y minus k. That would be the difference in y. But in this case, I did make it so that the coordinate up here is higher than the k over here. But what if we had a situation where this point was below this line? I mean, there's nothing here that I've said that we can only deal with points above this line. We haven't proven that to ourselves yet. So to make sure that this distance is positive, we could take the absolute value, or we could just square it and then take the square root. And then that ensures that we're not dealing with negative distances. So here we've set up the equation for all of the x's and y's where the distance to the focus is equal to the distance to the directrix. And let's see if this actually turns out to be a parabola. So the first thing we can do is we can square both sides and get rid of the radicals. So we get x minus a squared. Radicals aren't good. Well, I don't want to make any social commentary. So x minus a squared plus y minus b squared is equal to, square the other side, y minus k squared. And right now, at least, it looks like there's going to be some y squared terms, and we know, there's definitely an x squared term. That doesn't seem like it's a parabola right now, but let's keep going forward. So this is x minus a squared, and then let me square these. Let me actually expand these two binomials. So plus y squared minus 2yb plus b squared is equal to y squared minus 2yk plus k squared. And what can we do to simplify this? Well, we have a y squared here, and we have a y squared on the right-hand side. So we can subtract y squared from both sides of the equation. They cancel out. And then we got rid of the y squared. So all of a sudden, this is starting to look a lot more like a parabola, because we have this is now an equation that relates y's to an x squared. So let's clean this up and actually make sure that we can get it in a form that we normally associate with a parabola. So we now have, I'll just rewrite it, x minus a squared minus 2yb plus b squared is equal to minus 2yk plus k squared. Now what can we do? Let's take all the y's and the constants on one side of the equation. So if we move both of these terms onto the right-hand side, so we want to add 2yb to both sides, so we get x minus a squared is equal to, I'm moving both of these terms to the right-hand side. So if we add 2yb to both sides, then we'll have a positive 2yb on the right-hand side, so 2yb, and then we'll have that minus 2yk right there, minus 2yk. And then we're subtracting b squared from both sides. So it's minus b squared plus k squared. I just arbitrarily decided to write whatever I transferred from the left-hand side to the right-hand side in magenta, just so maybe it makes it a little bit clearer. And let's see if we can simplify this further. And remember, and just so you know what I'm doing this whole time, in the back of my mind, I'm trying to get it into the format that is very that I normally associate with a parabola, and I'll do it in the corner here, just so you know where the algebra is going. I'm trying to get into a format x minus a squared is equal to y minus b. Because if we have it in this form, or actually ax, let me rewrite that because I went too far to the right. A times x minus, well, actually, I already used the a, so let me write x minus, I don't know, I'll make up x minus, I'll call that, I don't know, v squared. I'm picking maybe v for x value of the vertex. I don't know, I'm making up variables on the fly. A times x minus v squared is equal to y minus b. And the actual letters I choose don't matter, but this is a general form of a parabola. And this is where I'm trying to go. If I can get this thing that we're working on to this form, then we know we're dealing with a parabola. And then we can actually relate what we normally associate with a parabola to these terms up here. And obviously, these are different letters than these letters. And then we can try to figure out, if we have a parabola, how do we figure out its focus and its directrix. But anyway, that was a bit of an aside, just so you know where we're going. So let's try to simplify this a little bit more. So we get, my phone is ringing. Oh. Let me silent it. So we get x minus a squared is equal to, let's see, if we factor out a 2 and a y, we get, let me factor out a y first. We get 2b minus 2k times y. And then I want to make it minus some constant. So this is a constant right here. This is one constant squared plus another constant. So I could make this equal to minus, let me think about this. This would be minus b squared minus k squared, right? If I expand this minus out, you would get minus b squared plus k squared. So this is the same thing right there. And let's see, can I factor out? Yeah, I can factor out a 2. So then I get, the whole thing becomes x minus a squared is equal to 2 times b minus k times y minus, and now this is the difference of, this is b plus k times b minus k. You might want to review the factoring polynomials, or factoring polynomials if that doesn't look familiar. But this is b plus k times b minus k. And I wanted to do that because I saw this b minus k out there, so that looked interesting to get it on both terms right there. And let's see, if we divide everything times, let's divide everything by 1 over 2b minus k, because I just want a y here, so I have some coefficient in front of the y. So let's divide everything by 1 over 2b minus k. So then you get 1, let me do it down here so I have some space. 1 over 2b minus k times x minus a squared is equal to, well, I'm dividing this by 2b minus k, so that goes away. So it's y minus, so if I divide this by 2b minus k, the b minus k's cancel out, and I'm just left with b plus k over 2. And I think I have gotten it in the form that I wanted, right? In this case, the a that I wrote up here is now 1 over 2b minus k. This v is this a that I did here. The y is the y, and then my constant term is out here. So I have hopefully shown to you that the locus of all points that are equidistant to this point, which is really just an arbitrary point, I said it's the point AB, and some line is in fact a parabola. And that's one of the ways that people define a parabola. And we'll actually see soon that when you actually change this relation, in this case, we found all of the points that are equidistant to the focus and the directrix. If we change that ratio, if we find all of the points that are half as far away from the directrix as the focus, we start getting another conic section. If we said twice as far, we would get another conic section. So this is a very interesting way of relating. Sometimes the conic sections in the first video I showed how they're all related to cutting the three-dimensional cone, but they're also related in this way. And eventually I want to relate this to the three-dimensional cone so you can see how it all fits together, which is always the fun thing about mathematics. So this, so far, all we've shown to you is if we do take the locus of all points that are equidistant to a point and a directrix, that it is a parabola. Now the interesting thing to do is, let's say I have a parabola. Let's say I have a parabola, and let me give a general form. And I'll try to use different letters than I used up here. So let's say I have a parabola y minus, let's call it y1, right, where it's just a particular point on the parabola, y minus y1, or you could call it some constant, is equal to, let's call it, I want to use a capital A just because that tends to be the, well, I use a capital A, and just know that it's different than this lowercase a. Some capital A times x minus x1 squared. Whenever you see a y sub 1 or an x sub 1, that means you're actually dealing with a constant term. If you see just an x or y, that generally means that you're dealing with a variable term. So these are constants. I could have put letters there. I could have put a and b there, but then that would have gotten confused with that. But let's see if we can relate these letters, because this is something that we normally see, and then we want to find the focus or the directrix of a parabola like this. How can we relate these to these values right here? How does k and a and b relate to these right there? So let's see if we can set that up. So if we just pattern match, that is a. If we say x1 is lowercase a, actually that's a straight up pattern match, so we can already write that on the side. x1 is equal to a. So whatever x value you have here, this is also the x value of the focus point, which makes sense because in this case, we already learned this in the previous video, but we learned that the vertex of this parabola is the point x1, comma y1. Anyway, I don't want to confuse you. Actually, you know what I'm going to do? I don't want to go too far off into this topic, and I think this video has already gotten long enough. I will continue this in the next video. See you soon.